Going to continue on here, chapter 17. Sounds good. So earlier this morning, we talked about redox reactions. And again, our oxidation, basically going to lose electrons. Our reduction will gain electrons. And as we talked about, as we did a number of examples, we can again use sort of just a basic number line. If you can identify, obviously, the oxidation states that we talked about of everybody that's involved. And again, if you find yourself moving towards the positive direction on this number line, when you look at the oxidation states from reactants to products, your guy is basically getting more positive, which means it's losing electrons and it's going through oxidation. If you are sort of traveling in the opposite direction towards the negative side, it doesn't really matter if you completely get to negative or not. It will be a reduction reaction that will take place. Remember, we also talked about our oxidizing agents and our reducing agents. Our oxidizing agents are, again, the substances that get reduced. Our reducing agents are our substances that get oxidized. And as we talked about earlier today, again, they're called that because that's pretty much what they are causing in the other reactant, for example. Again, in order for somebody to gain electrons, somebody has to lose electrons. So the reducing agent would cause basically somebody to lose those electrons so that they can gain them. And vice versa there. So the oxidizing agent would cause the oxidation of somebody so that they lose electrons, so they get reduced. Let me say that correctly this time. And the reducing agent, obviously, here will cause somebody to gain electrons. So it's going to be oxidized and lose electrons. Again, those are two different questions as we talked about earlier: what's being oxidized, what's being reduced, and the oxidizing agent, reducing agents. We talked about oxidation states, and really oxygen is a good place to usually start. And again, that's -2 in most cases. Again, if you have sort of a 3-pack of elements, kind of go on the outside, leave that center guy usually for the end there to assign the oxidation states. When we balance basic half reactions where we have an oxidation and a reduction half reaction, again, in the oxidation half reaction, electrons should be on the product side like they're being lost. In the reduction half reaction, they should be on the reactant side like they're being gained. And when we add these guys together, these guys should always completely cancel out. So as we saw, you may have to multiply a half reaction by a common number, or maybe both of them by common numbers to do that. We talked about, obviously, there at the end, balancing more complex sort of redox reactions in either acidic or basic solution. And as we saw, really, regardless of which one you're doing, really just take the acidic approach and go all the way through. And then obviously, if you need the acid reaction, you put a box around it. If you need then the basic sort of reaction, all you have to do, again, is to convert it at the end by adding OH minus to both sides, equal to the number of H pluses that you had in your final equation. That, again, is how you know if you look at a balanced redox reaction, if it's balanced in acidic or basic conditions, is you should have H plus if it's acidic conditions. And obviously at the end there, as we saw, you should have OH minus in that reaction or equation if it's balanced under basic conditions. Remember, in order for it to properly be balanced, those two things need to be sort of met, and that is, again, you should have, I'll go back too far. There we go. You should have the exact same number of elements on each side, like a normally balanced equation. And again, the overall charge on each side does need to equal each other, and it does not need to be 0, but need to have the overall same charge. Any questions on any of that stuff that we talked about earlier today? I guess it was. Yeah. All right, then let us continue to really the heart of this chapter, which is talking about sort of galvanic cells. And galvanic cells are basically redox reactions that are taking place. And there's an oxidation part, obviously, and a reduction part that's occurring. So this is a traditional galvanic cell, like one you can build in the lab. which they don't have you build one like this anymore, but you could build one like this if they still did. So this is the basic sort of components of a galvanic cell. We have one side over here, beaker, and inside the beaker we have an electrode. In this example here, we have zinc electrode. We will also have zinc ions floating around that solution. So in this example, they have some zinc sulfate floating around, which will give us really the ion version of the electrode. So usually when you're sort of building your galvanic cell, your solid electrode, you would then have this similar metal ion there floating around in the solution like we do here, which is our zinc. Then we have on the other side another beaker. In this example, it has copper. And in the solution there, we have some copper ions floating around in this particular case of the copper 2 sulfate solution. Left-hand side in this example is what is referred to as the anode. And the anode is where oxidation occurs. So we're going to lose electrons. The electrons will travel through the wire that's typically connected between the two sort of parts of the cell. And you'll get some voltage there as the electrons go through and pass through towards our cathode side. And on the cathode side of the galvanic cell, that is where reduction takes place. So what is happening essentially in this is our solid zinc that is pictured here in the super zoom picture of it. The solid zinc are going to lose electrons. So they go from an oxidation state of 0 to where they will then lose some electrons and have a +2 charge. So what that means is essentially these guys are in the solid state, will go off and go for a dive into the pool there, and they will form some zinc with a +2 charge as they do so. The electrons that travel through the wire to the other side will actually then kind of hook up with the floating copper ions. And those electrons will come together. And those guys will decide it's time to get out of the pool. And they will come out of the pool there and basically become a solid at that point. So things with a positive charge usually are found in the solution part. Things with no charge are obviously solids in most cases. So we have basically a redox reaction that's happening. We have on this cathode side, as you can see from the half reaction there, we got our copper plus a couple of electrons going to make some solid copper. And obviously, this guy is going to give off a couple of electrons here. And this is essentially what is taking place in this galvanic cell. This is pretty much similar to, as we'll talk about a little bit, batteries, how they function. You plug them in. I guess you don't plug batteries. I guess you do. You plug your battery in. I guess you do nowadays with a car. You can plug your battery in. But you put your battery into your device, and obviously there's wires in the compartment, right? So this redox reaction happens. Those electrons go out, and they could do some type of work, like power your device, and those are what it's used for in this particular case here. Other important parts of this galvanic cell is actually the salt bridge. And the salt bridge here is really important and is usually filled with some type of electrolyte, like a salt solution like we have here, potassium chloride sort of happening. So the idea here, as we'll talk about with a galvanic cell, is electrons are negatively charged. So there is sometimes referred to as like a potential difference between the anode and the cathode. You could think of it like the cathode's more positive-ish, if you will, and that helps bring those negatively charged electrons towards it, right? It's going to be kind of attracted to it, right, as opposites attract. So the salt bridge is really important to keep everything running correctly. So why would that be important? Well, if we, for example, take a look at this cell here. So we had on this side basically our zinc and our zinc 2+ floating around, coming around. And we go this way down to our copper and our copper 2+ basically floating around, right? So this is our galvanic cell, and I decide I'm going to basically just pop out. And obviously we had sulfate, I think in this example. Was there other ion here? I'm gonna just pop out my salt bridge and just let this thing run, right? So what's going to happen is as this cell starts to run, we are obviously building up over here zinc ions, right? They're going to top off the solid, right? And we're going to build up a bunch of zinc ions in that solution. On the other side, we have a lot of copper 2 ions that are going to kind of come out of solution, right? Which will leave us our negatively charged ion floating around, right? So what happens is if you were to take the salt bridge out, because the zinc guys are floating into the solution, what you're essentially going to be doing is on the anode side here, you're essentially just going to be building up positive charge from all those like zinc ions that are pulling in there. And on the copper side, because all those copper ions that were originally floating around in the cathode side over here are going to basically leave the solution, on this side, you're going to build up a bunch of negatives, right? And this would be the situation, right, that would occur if you let this galvanic cell run without the salt bridge present. Now, why would that be troublesome if you want your electrons to go that way? Yeah, what's going to happen is now they're going to go, whoa, I'm like kind of more attracted to the positive guys over here. Not so much happening over here is super negative. Nobody wants to go that way. And your cell's now going to basically stop functioning, right? And it's not going to work really well. So that is really the function of the salt bridge. Because the salt bridge, for example, in this case, has potassium chloride, if we put in our salt bridge, which was potassium and chloride, what's going to happen is the potassium now is going to shoot this way and the chloride is going to shoot this way. And that is going to basically knock down the buildup here, right? Of those negative charges and also knock down the buildup of the positive charges here. And that's why you see in that picture that the chloride is actually heading to the left there and the potassium is heading to the right, again, to keep that buildup from happening. So you do want a slight difference in sort of the buildup of the charge to allow those electrons to flow from the anode to the cathode. But you take the salt bridge out, you're going to get the buildup of charges wrongly for your what you want to do. You're going to build up too much positive on your anode side, which is not going to let those electrons go anywhere pretty much. They're just going to hang out there, and obviously your cell will stop running. So that is the purpose of the salts bridge, is to really keep everything flowing correctly. And the way it does that is, again, to prevent any real buildup of positive charge or negative charge on one side of your galvanic cell, which would obviously stop the flow of electrons from one way to the next. Any questions on that there? So obviously here you could use a tube that would connect to two beakers. You put some cotton in there, which does allow obviously everybody to flow in and out, almost acts like a membrane, but keeps the entire solution from falling out basically. But again, it keeps that charge sort of built up from building up. So those are the main parts of a galvanic cell. Anode part where we have our oxidation occurring. Cathode part where we have our reduction occurring. Salt bridge, very important to keep everything flowing so we don't get basically the stop sign happening. And again, those electrons that are flowing from one side to next, always from the anode to the cathode. In the case of a galvanic cell, again, that voltage can be used for something to do some type of work. As we'll talk about, usually positive voltage is good. That means kind of the cell's running good. Negative voltage, not so good. Also, very similar to a battery. If you put the battery in correctly, it works, right? Flip it around, not so much. You just made it non-spontaneous, so it's not going to work. So it works kind of similar to that. Any questions on the galvanic cell here? So you do need to know, obviously, what a galvanic cell looks like, the different parts of it, in case I ask that question on the test, which I'm probably going to ask, I imagine. So make sure you know that. All right, so let's talk a little bit more about galvanic cells and some of the things that we can calculate. Here's an actual picture of a galvanic cell that you could put or build in class. It's kind of hard to see there, but right about there is your salt bridge that kind of connects the two. The difference in electrode potential, again, is what allows really those electrons to go from our anode to our cathode. That's sometimes referred to as the cell voltage. And a volt is 1 joule of work per coulomb of charge that's been transferred. So 1 volt equal to a joule over a coulomb, and that conversion we'll see a little bit down the road as well. It's also sometimes referred to as electromotive force, EMF, and cell potential. So sometimes in a problem, you may be asked to calculate one of those 3 things: the cell potential, the cell voltage, or the EMF. Basically, what they want you to calculate is the cell voltage, is basically what they're asking you to do so for that cell. So if we look at the overall reaction that's happening here, which is the net ionic equation that we got going on here, obviously in the example that we just saw in that picture, the sulfate's a spectator ion. In that case, it's just kind of floating around. It is, in this case, our zinc, which once again is going from an oxidation state of 0. Our copper has a +2 oxidation state to 0, and our zinc going to +2. So once again, our zinc is becoming more positive, so it's being oxidized. Our copper here becoming more negative, is being reduced. We can write what is sometimes referred to as a cell diagram, and that is what we see here on the bottom. This is a cell diagram, and it's always written like this. This first part of it is the anode compartment, and the second part of it is the cathode compartment. The 2 lines here usually represents the salt bridge in this particular case. So how are these usually written? Pretty much like this. It usually is reactants separated by a line, products, reactants, products. And you can see that here's our reactant, there's our product, there's our reactant, and there's our product. So that's usually reactant, product, and that's sort of a shorthand of how we can write our galvanic cell. You can see it included in here, and sometimes they will include the molarities. Also, you can, as we'll talk about, have sort of a galvanic cell where one of your components is a gas. So you might also see pressure sometimes written in the cell diagram as well. So again, that is pretty much how you could go from a cell diagram pretty much back to the reaction or equation. It's basically that order there, and balance it up and all that kind of stuff. Any questions on that there? So let's talk a little bit about how we get these values that we're going to use. First off, the values that we use when we are dealing with galvanic cells, they're sometimes referred to as standard reduction potentials. That is sometimes abbreviated as an SRP, for standard reduction potential. So in this particular cell here, we have the anode, which is our zinc. And once again, in this situation, our zinc is going to go for a swim and become zinc +2. In this case, our H+ that's floating around is actually going to come out as hydrogen gas. In this case, that's the bubbles that you see happening in that case when it gains electrons. And overall, it is, again, our hydrogen that is gaining those electrons and being reduced, as we can see here in the half reaction, going from +1 to 0, so becoming more negative, and our zinc going from 0 to +2, becoming more positive and being oxidized, giving us our overall reaction. And as you can see here, they included the 1 atmosphere, which is standard pressure, because in this case, hydrogen is a gas, so it's being basically bubbled in there through the electrode. You will also see that there is no hydrogen electrode. They are using platinum in this case, which sometimes does occur. So sometimes they'll use platinum or any type of metal like graphite or something like that, where it's sort of the physical application of the electrode because the actual electrode's a gas. And that also finds itself included in the cell diagram. So once again, if we look at this, this is our reactants, our products, our reactants, our products. So again, there's our zinc and our zinc with a 2+, our H+, and our hydrogen, which is our product. So again, that is how we get from the cell diagram to the equation. As you can see here, they will include the platinum in this case in the cell diagram. but obviously it's not included in the overall equation because it's not really doing much other than being the physical sort of electrode in this case. Any questions on that there? So how does this help us? Well, this helps us by, as you may know, a lot of times in chemistry, when we cannot measure something directly, a lot of times what they do is they will pick something to use as a standard, and they'll pick something to use as a standard to compare everybody else to. And when we want to calculate standard reduction potentials, which is abbreviated with this E in the knot, and we'll see a table of all these values, basically. These are all basically written as reduction reactions because that's what it's called, standard reduction potential. So they chose the hydrogen electrode as the standard to compare everybody to, and that is sometimes referred to as the SHE for standard hydrogen electrode. And they gave it an SRP of 0 volts. So they kind of randomly gave it a value of 0 volts. And the half reaction for that, as you can see, is a reduction half reaction as the electrons are on the reactant side. And it's gaining our two H pluses to make our hydrogen gas. So basically what they did is they assigned this guy a value of 0 volts. And now what they can do is pretty much take that hydrogen electrode and hook everybody else up with it and get some voltages of the cell. And they'll be able to calculate what is the standard reduction potential for different elements along the way. So they did that, for example, here when they hooked up the hydrogen and the zinc together. And when they hooked up the hydrogen and the zinc, they ended up getting a cell voltage of 0.76 volts when they did it. In this particular case, our zinc is our anode. And the hydrogen electrode there is our cathode in this case. And our electrons are traveling from one side to the next. So to calculate the standard EMF of a cell or the cell voltage, you could use this equation right here, which is E of the cell is equal to E of the cathode minus E of the anode. So I'm now going to explain something that will not make sense probably right now, but will hopefully make sense a little bit later on as we get there. So just nod your head as I'm explaining it to you and it should be okay. So if you use this equation, you should use it exactly how it's written. And when you go to the table, which is where you typically will find these values located in a table, you should not change the sign of the values that you find in the table. And the reason you would not do that is because the negative is here to basically change the sign for you. Now, correctly speaking, when you go and do one of these reactions like we look at here, it is a redox reaction, which means that there should be an oxidation reaction where the electrons should be on the product side, and there should be a reduction reaction, which means that the electrons should be on the reactant side. The problem is, in a sense, I don't know if it's necessarily a problem, but when you go to the table, the SRP table, that again stands for standard reduction potential, which means when you go to that table, the only type of reaction that you will see in there are reduction reactions, which means they will all have electrons over here, which is great, except that when you're actually doing your reaction, one of those reactions is actually a oxidation reactions, which is actually the reverse of the reaction that you would find in the table. And that means that you, technically speaking, should flip the reaction around. So if we look at, for example, the zinc SRP value that you would find in a table for zinc, this is what you would find. You would find that the zinc plus a couple of electrons equals the zinc with no charge, and it has a SRP value of minus 0.76 volts. Now, technically speaking, that works great if zinc is my cathode. In this particular example, zinc is really not my cathode, it is my anode, which means the real reaction that's happening on the zinc part is actually the reverse reaction. It is the zinc going to zinc with a +2 charge and a couple of electrons. And because it is technically the reverse of this reaction, the oxidation half reaction would actually have an E value of positive 0.76 volts. And that's sometimes referred to as a standard oxidation potential there because it's the oxidation half reaction. So when you do write half reactions and you do sort of display the E value there, it should be specific for how the reaction is written, which means I actually changed the sign myself, which brings us to the second part of this is you will sometimes see this equation written E of the cell is equal to E of the cathode plus E of the anode. And that is a plus versus a minus, yes? So what I'm going to say now, which again may not make a heck of a lot of sense yet, is if you go to that table, because they are all technically written as reduction reactions, you technically from that table should reverse the reaction that you find there for the anode side. And you should also change the sign that you see in the table because that's what should go with the anode reaction. If you do that, which is, I guess, proper for giving all that, you should actually add the values together because you changed the sign. If you don't want to have to worry about changing the sign yourself, just take the values you find in the table, and the minus in that first equation will change the sign for you. And that makes absolutely no sense to anybody at this moment, right? But again, if you are going to subtract, just remember this, if you're going to use the subtract version, and I would pick a version of this equation and stick with it, either the subtract version or the added version where you add them together. If you're going to subtract, you do not need to change the sign, just take the values as you find them in the table. If you want to add them together, you need to change the sign for the anode one. And again, we'll do some examples where that will be maybe a little bit more clearer. So for example, when you look in your lab manual, I believe they use the one where they add them together. And they assume that you're going to change the sign yourself, so you should add them together. But you can use the minus one and not change the sign, and it will change it for you. Good talk. All right, so now back to this, and again, we'll do some examples in just a second to sort of see what I've been talking about here. So if we put this cell together, we do get an overall cell voltage of 0.76, and we can figure out our value of our anode in this case, and it ends up being an SRP value of minus 0.76 volts for zinc. And we get that by essentially putting it into this equation where the cell itself had a 0.76 volts. Our cathode, which was our hydrogen, is 0 volts. So the E of the anode, which was our zinc in this case, we would move the negative to the other side. And that is, again, how we get to that number right there. Now, if we hook up this hydrogen electrode with copper, we get a reaction that looks something like this. And what we see is, in this particular case, the standard hydrogen electrode is actually our anode in this case. And it is the copper that is our cathode in this case. And this illustrates a really good point. Anything could be an anode or a cathode. So anything has the potential to be either one, the anode or the cathode. In some cases, it may work. In some cases, it may not work very well. But things can be either anode or cathode. So in this case, what's happening is the hydrogen is going to be losing some electrons. So it's going to go from 0 to +1. So it's going to toss its electrons out and drop into the solution some H+. Those electrons are going to come across here and hook up with our copper that's in the solution. And this guy is going to come out of solution as a solid in this case, going from +2 to 0 and being reduced in this particular case. And they did the same thing. They hooked this up together, and overall they got a cell voltage of 0.34 volts. So if we put that into our equation here, and our anode again is going to be our hydrogen in this case, we will get a SRP value for copper that is 0.34 volts. And again, the overall reaction is what we see down there on the bottom. And once again here, because the hydrogen is a gas, we have the solid electrode that's not going to be used, but this is our reactant, our product. There's our reactant, there's our product, and this is our reactant, that's our product. So reactant and product, again, from our cell diagram as to how that turns into an equation. You obviously, as you see there, might have to do a little bit of balancing out of the cell diagram to make sure everything is balanced for the overall equation. So let's take a look at a table of SRP values, which clearly this is similar to one in your book, and you should memorize all those values, which you could clearly see. I'm just kidding. I'm just kidding. They're like, when's that drop date? Is it now? Or is it going to drop now? No, you obviously it will be provided to you. Yes, if you need it. So let's talk about a little bit about these values and stuff that you would see there. I don't think the zoom helped all that much, but when we look at all these guys, let's go back to the other, maybe that one's a little bit easier to see. When we look at all these reactions, this is an SRP table, and again, you can see they are all written as reduction reactions, and as we just talked about, pretty much you would need to sort of flip one around. So let's talk about if we had a zinc like we had before and a copper, and I think originally this guy was our anode and this guy was our cathode. So let's say we had that galvanic cell like the one that we had at the very beginning picture there. We would go to this table and we would obviously find our zinc reaction, which again is our zinc plus our 2 electrons, making our solid zinc. And it has an E value here of minus 0.76 volts. We could also find our copper 2, which was on here right about there. There's our copper 2, which is our copper plus 2 plus a couple of electrons, going to make our solid copper. Has an E value there, as we just saw, of that's calcium, which is kind of close to it's kind of close to copper, but not so much. When we go up on right there, I hope it's copper. That's to copper 1. When we keep going, I can keep putting in arrows. There's what I'm looking for right there. That's going to be an E value there of 0.34 volts. I know it's like an eye test a little later on. That'd be okay. Maybe I should have zoomed that out. Yeah, there we go. All right. Also brings up a good point, which is why I did it. But you make sure when you go to the table, you find the right thing, right? Because obviously this is not solid copper at the end. That is copper with a +1 charge. And clearly, I don't know who was putting arrows down here at calcium. That clearly is nowhere near what copper should be. All right, so let's take a look at if we were going to calculate our E of our cell. And if we wanted to add this reaction together, let's just first talk about what happens if we wanted to add this reaction together. So if I wanted to add this together, my zinc is my anode, which means this reaction is not written correctly, right? Because that is a reduction reaction. So I would technically, again, need to flip my reaction around. And that would be my anode reaction, right? Which is an oxidation reaction. My copper, though, is okay because it is a reduction reaction and it's written as a reduction reaction, which means I could leave my copper guy just the way it is. And now I could add these reactions together, right? And my electrons should cancel, and they do, right? And just like before, if the electrons are not the same in each one, you do need to multiply to get them the same, but they will cancel. And it will give me my overall reaction of zinc plus my copper 2 going to my zinc with a 2 plus and my copper that's solid. So that would be the overall reaction that would be taking place in this case. And again, if we were going to calculate the cell voltage here, we have 2 options as to how we could calculate it. Option number 1 is I recognize that the zinc is my anode and the copper is my cathode. I could go into my E of the cell is my E of the cathode minus the E of the anode. And I'm just going to take the values exactly how I find them. I'm not going to change any signs or anything like that. So that means that I would take the cathode here, which is our copper, which is 0.34 volts, minus my minus 0.76 volts. And that's going to get me a 0.34 minus a minus 76. And give me 76. No, that ain't right either. 0.76 would be better. How about a 1.10 volts? And that would be the cell voltage that we would expect for this cell. So that is what I was talking about a second ago, where if you were just looking to calculate the cell voltage for this particular galvanic cell, and you're able to identify what is the anode and what is the cathode, you could go to this SRP table, and although they are both written as reduction reactions, you could take the values exactly how you find them, and as long as you subtract it, you'll be okay in terms of the voltage. Any questions first off on that calculation there? The other option is if you technically wrote your reactions like we have here, when I wrote my cathode or my anode reaction in this case, my E for that guy should actually change signs to positive 76 volts, because that is the opposite of my reduction reaction here, which is negative. So when you reverse one of these reactions, what happens to the E value is the sign changes. So it started at negative 0.76 in the reduction aspect of it, which means the oxidation is the exact same value, just the opposite sign, which would be positive. My copper, I did not do anything to it. It is exactly the way I found it, which means its E of the cell would be positive 0.34 volts. In this particular case, because I changed the value of my anode reaction, I do not want to subtract. I want to add in this case because I already changed the sign. So the E of the cell in this case would be E of the cathode plus E of the anode, because I already changed the sign, which would give me, again, my 0.34 plus my 0.76 volts will give me 1.10 volts as my answer. So if you change the sign, which is technically correct when you reverse the reaction that you find in this table for the cathode to make it into the anode, you should add those values together because you already changed the sign. If you don't want to deal with that, like I said earlier about changing signs, just take it from the table, subtract the two, cathode minus anode. It will change it for you, right? And then you'll get the same value there. Question on that there? All right. And again, I would probably pick a way and stay with it. That way you're not like deciding, should I add or should I subtract? The only thing you should not do, obviously, is change the sign and then subtract, because you'll just undo it, right? So don't do that, obviously, in that case. All right. So looking back at this table here, let's talk about some other things that happen in this table that we could do. The E is written for the reaction, or the value that you see is specifically for how the reaction is written. So obviously, as we've been talking about, these are all specific for the reduction reactions. So that is the E value that goes there. And technically speaking, if you flip it around, you should change the sign, which is basically what the third thing says there. The half cell reactions are reversible. And if you do reverse it, then you just change the sign. So if it was negative, it'll become positive. If it's positive, it'll become negative. The other really important value or thing that you could get from the SRP values is this. When you throw these two things together, how are you supposed to know which one's the anode and which one's the cathode? So you could use the SRP values to help you decide that. And the one that is more positive has a greater tendency to be reduced. So the anode or the cathode, which one gets reduced? It is the cathode. So if you're told you're building this galvanic cell out of these two things, and they don't really tell you which one's the anode, which one's the cathode, you should go to this table, and whichever one has a more positive value for their SRP will be your cathode, and the other guy will be your anode. So again, this would mean that that would be your cathode in that case. There's a very important aspect to that you do have to keep in mind, which is if they actually do tell you what's happening in the reaction, or they give you an equation, you have to look at it and see what's happening. You have to see who's being oxidized and who is being reduced. So if they give you any information in the words like this reacts with this, or here's the overall reaction that's happening, you need to look at the equation or what they tell you and figure out who's being oxidized and who's being reduced. And that will tell you which one's your anode or cathode. Obviously, the one being oxidized would be your anode. The one being reduced would be your cathode. If they simply don't give you any of that information other than, hey, you built a galvanic cell out of these two things, then you should go to the table. The more positive one will be your cathode. Any questions on that there? The last thing is, as we talked about, sometimes you may have to multiply one of these reactions or half reactions by a number to get the electrons to cancel out. It has no effect on the E value. So if you had to multiply somebody by 2 all the way across, your E value stays the same. You do not multiply it by it. So that's different than things like delta H or things like that. So if you multiply, divide, whatever it may be, you do not have to multiply the E value. It just stays the same as you find in the table. Any questions on that there? All right, that's a lot of words. Let's just do some maybe. There we go. All right, what is the cell voltage here for this galvanic cell? Why don't you also write the balanced equation? These are obviously the SRP values you would find in a table that's given to you there. So balanced equation. Okay, so let's take a look. In this case, we have a galvanic cell. We want the cell voltage. We also want to balance it up. So we want to figure out which one is our anode and which one's our cathode. Again, we would go to the SRP table that we just saw there and pull out both of these things, the reaction there and our SRP value. And we would analyze them. And now you will tell me the one that will be the cathode is. It would be cadmium. I was going to say not everybody at once there. That would be the cathode, as minus 0.4 is more positive than minus 0.74. They're both negative, but that's more positive. I'm sort of positive of that, I think. Yeah. So that would by default mean that the other one would be our anode. So again, we could use the SRP value to help us. They did not really tell us how this thing's reacting or anything like that, or who's the anode or her cathode. So with the lack of any information about how it's happening, we would go by, again, the more positive would be our cathode. Since we did want to balance the equation as well, that means technically speaking, the anode reaction is not written correctly. It is backwards, right? Because it's a reduction reaction, which means technically speaking, we should flip this guy around. And when I do that, my SRP value will now go from minus 0.74 to positive 0.74 as we flipped it around. Any questions on that there? Now that I have my equation in the right orientation, I can now add both of these guys together, but wait, I cannot do that yet because the electrons are not the same in each of them, right? So we do need to actually multiply each half reaction here by a number. So this guy will need to be multiplied by 3 to get to 6. This guy here would need to be multiplied by 2 to get to 6. So I'm going to do that underneath. That will get me 3 cadmiums plus 6 electrons gives me 3 cadmiums. Now I multiply that by 3. What happens to my SRP value? It stays the same. It's, again, unaffected by multiplying by that number, so it'll be the same. We're going to multiply the bottom guy by 2 there. It's going to give me 2 of the CRs, 2 of the CR3 pluses, and 6 electrons. And much like the other one there, it's going to be unaffected by multiplying in this case. Now I have both half reactions actually balanced. Our electrons should cancel out, which they do, and that would leave us our overall equation, which will look something like this. And by the way, just like any redox reaction like we were doing before, this should be balanced the same two ways. If I don't erase it, 3CD, there you go. We have 3 cadmiums on each side, right? We have 2 chromiums on each side. Overall charge on the left-hand side is +6. Overall charge on the right-hand side is +6. So that is the properly balanced equation for this reaction that is taking place. Any questions first off on how we get there? Yeah. Yeah, you will have to, if you had, so I'll answer this 2 ways. You will have to reverse the anode equation if you need to do something like this, where you need to really write the overall reaction or sort of put them together. It will always be the anode, because that table is an SRP table, which means everything in there is a reduction reaction. That's what the R stands for in the middle. So it's the standard reduction potentials. So every equation that you see in that table with values will be a reduction reaction. Yeah. Other questions? Okay. So now it comes to really what the real question asked was, what is the cell voltage here? So at this point, you really do have 2 options. Because in this case, I did change the sign here on what I did on the bottom here, I could do the E of the cell would be adding those 2 guys together. Again, with my positive value here, because I already changed the sign. And that will get me minus 0.4 plus 0.74. And that's going to give me a 0.34 volts. The other option is, if I really didn't have to do the balancing the equation, which is really what the real question asked, I could just identify, like I did at the very beginning, that this guy was my cathode and this guy was my anode. And I could go into the E of the cell is our E of our cathode minus the E of the anode. And again, here, if I was going to do that, I would not change any signs. So this would be minus 0.74 volts. And again, that negative will change the sign for me. And we will end up with the same, obviously, correct answer here of 0.34 volt. So again, this is what I was talking about earlier, where if you are going to not want to worry about changing signs, just take them exactly from the table and subtract them. If you want to change the signs, then you can change the signs, but add the number. Any questions? Yeah. Yes, it can be. Yeah. So the E of the cell can be negative. In this case, it's positive, and that's what we'll see. Actually, a positive value for E of the cell, or a positive voltage, it means really like a spontaneous process going to occur. If you have a negative value for E of the cell, then it's basically going to be a non-spontaneous process. Again, very similar to like your battery went in correctly, it works. Flip it around, you just made it non-spontaneous, so it's not going to work. So it's kind of the same idea. Other questions on that? All right, so let's take a look at another one here. Galvanic cell consists of magnesium and silver. Calculate the cell voltage here as well. Okay, so let's take a look. Once again, they're not really giving you any information about how this reaction is taking place. So we could go to our SRP table there, look up these values. And once again here, this guy looks more positive than me. So I'm going to say in this case, our cathode should be our silver and our anode should be our magnesium in this case. So again, right off the bat, as I mentioned before, if you're just really looking for the cell voltage here, you can just go right into that equation where we subtract our cathode minus our anode. And in this case, we again would not change our sign. So 0.80 volts minus our minus 2.37 volts, going to give us 3.17 volts as our cell voltage. So again here, although technically speaking, that one should change, I'm not going to change it because the minusing will do that for me. Any questions on that there? We did want to balance the equation, so we can do this. So Our anode equation is the one that should flip around. So that would get us basically magnesium going to magnesium plus a couple of electrons. And now since we did flip it here, the E for this cell or this equation should actually be positive 2.37 volts. Our cathode is good to go because it is the reduction, except that we really don't have the same number of electrons, right? So before we move it over, might as well multiply this guy by 2. That way we'll end up with the same number of electrons, and that would give me 2 silver ions plus 2 electrons will get me my 2 silvers. And again, I did not change anything here, so this will still be our 0.80 volts. Now we do have it in the proper way to add them together. Our electrons will cancel. That will give us the overall reaction that's happening here of magnesium plus 2 silvers. Go to magnesium with a plus 2 charge and 2 solid silvers in this case. Now, again, if you went this approach first and you decided to change the sign to get the E of the cell at this point, we want to add these values together, and that will again give us our 3.17 volts. Any questions on that? So hopefully it's becoming a little bit more clear what I was trying to mumble there earlier about change the sign or don't change the sign and make more sense now. I promise you it would, I hope. Yes. All right. I know, but it's fun just to do it earlier and people go, what are you talking about? All right. Any questions on either of those? So again, if you really don't have to write an overall reaction or anything like that, sometimes it's just quicker to subtract, just take the values from the table and pop them in there. All right. Let's then talk about some other things that are related to each other. Our cell potential, our electrical work, and free energy. And that's our good friend delta G, right? From chapters of the past there. The work that can be accomplished by electrons as they kind of go through the wire there can be used to do some type of work, as we mentioned. So 1 joule of work produced between basically a difference in charge, which is basically what you have in a galvanic cell, that potential difference between the anode and the cathode. Cathode sort of being a little bit more positive. You want to think about that way to sort of drag the electrons across the wire will result in our 1 volt of potential. Really the maximum amount of work that you could do, and that is what the W stands for here, work. And obviously that's energy and our heat, our charge, and is basically equal to our delta G, which is our Gibbs free energy. So I'm assuming there's got to be a formula that relates those two together. So let's talk about that. And there it is. There's the formula. So our delta G is equal to minus NFE. And that is our relationship between our thermodynamic properties and our cell potential. I'm just going to scroll this and we'll talk about all this here in just a sec. There we go. All right, so let's first talk about our delta G is equal to minus NF of E. That is our Gibbs free energy is equal to minus N. That is the number of moles of electrons that are happening in this reaction. So first, let's talk about N and the proper way to do N. So if I have an oxidation part of the reaction where it loses 2 electrons, and then in the reduction part of the cathode, it gains 2 electrons. The N value in this case is 2, not 4. So you do not want to add them together or anything like that. So it is the total number of electrons that has been lost by somebody, which should be the same total number of electrons that has been gained by somebody. So from your balanced half reactions, whatever that E value or electron value is just the one number. Don't add them together, which is again a common mistake that sometimes people will make. F is our friend Faraday's constant, which is 96,484 bar 96,500 joules per volt per mole, and that's also sometimes a coulomb per mole, and that's because a joule over a volt is equal to a coulomb. So that is the relationship there. E of the cell is our cathode minus our anode. So that is our whichever version of that equation you like to use. Our cathode minus our anode basically is our E of the cell. So let's talk about what happens in each of these situations when we look at this equation. If I have a positive cell voltage, like we were talking about, when we look at this equation here, our minus NFE. If this guy is a positive value, Faraday's constant is obviously positive, and the number of moles should be positive. That's going to result in a delta G that's going to be, if I wrote G, it was going to be negative. So that delta 6 is going to be negatively charged there, or negatively signed, and a negative delta G means the reaction is spontaneous, right? So a positive cell voltage will result in a negative delta G, which means that the reaction should be spontaneous and that galvanic cell should go. And we should be heading towards the product side there, and the overall reaction is taking place. Opposite is true if we look at this in the opposite direction. If we get a negative cell voltage, our Faraday's constant is still going to be positive. Our moles are still going to be positive, and we still have that negative in front. So 2 negative is going to turn our delta G in that case into a positive value. And that would mean that that reaction is non-spontaneous. So that's why negative cell voltage, not such a good thing. It means it's a non-spontaneous reaction, which means it's going to stay at the reactant side and no products are going to be made, and this cell's not going to really function correctly. So that is sort of the relationship between those two. Your cell voltage positive means you should have a negative delta G, should expect this galvanic cell to work. It should be a spontaneous reaction that should occur. If you have a negative E, should result in a positive G, which means it's probably not going to work very well, your cell reaction. By the way, if you put together a galvanic cell and you get negative voltage, how do you fix it? Yeah, just turn them around, right? So make your anode your cathode, cathode your anode, and before you know it, now you got positive voltage, right? So if you hook up your little alligator clips and you got negative voltage, unhook them and rehook them the other way, and then you will have your positive voltage that will happen. Any questions on that there? A couple of things you do still need to perhaps watch out for, maybe not so much. When you do solve for delta G in this case, you will end up in units of joules, as the Faraday's constants in joules. So that is the units that you'll end up with for delta G. As we talked about, usually delta G is given in kilojoules, so you might need to do a conversion factor there. Now, if we put that together with some equations from the past, because there's our favorite letter, K. If we put that together with our new delta G equation here and do a little rearranging, we get this equation right here, which is our relationship between the equilibrium constant and the cell voltage. And that E of the cell, again, is our cathode minus anode. That is our R, which is our gas constant. As you can see there, that's our 8.314 version of the gas constant. T is our temperature in Kelvin. N is our number of moles, and F is our Faraday's constant, and K is obviously our products over reactants, our equilibrium constant in this case. Now, if you happen to be at 25 degrees Celsius, pretty much that equation I put in a box right here will reduce down to pretty much this equation right here, which is 0.257 volts over N natural log of K. Or if you're a base 10 log kind of person, that would be 0.0592 happen divided by N, a log of K in this case. If you don't want to worry about either of those two equations, just remember the one in the box and just put the numbers in, regardless if you're at 25, which would be a much better choice, I think. So you can put those guys in there. A couple of things, though, if you are solving for K, you might have to do some inverse logging, right? And depending on rounding, you might get some slightly different numbers depending on where you round, and you kind of do that, but you should get the same answer. So this is our triangle of death here. If you want to know your E cell, your delta G, and your K, these are, again, our equations between thermodynamics and our E of our cell. So our delta G to our minus NFE And our one from our previous one, delta G is equal to minus RT natural log K, and then our E of the cell there. Any questions on those? All right. We kind of just covered this, but again, if we go into this, the nice thing about K is it pretty much is the same ideas as we talked about previously. So if you have a large value of K, you will end up with, again, a negative value for delta G. And obviously that would result in a positive cell voltage. If you have a small value of K, that's going to result in a positive value of delta G. And that would mean that you have a negative cell voltage. So all these things should relate to each other correctly in the sense. So if you're doing a problem with a large value of K, but you end up with a positive value of G, you mistook some negative sign somewhere along the way or something like that. So all those things just sort of agree when you're doing your calculations. So let's do a calculation, shall we? Calculate the delta G. Look, so our cathode in this case is copper is our cathode. And that is our anode in this case. We chose that because that's the wrong thinking, by the way, just so you know. You might be right.
You can't tell us that.
I'm going to tell you that one more time, just so you know. That's the wrong thinking, just so you know. And let me say it one more time. Still the wrong thinking after I thought about it some more. Still the wrong thinking. So although you are correct that this is more positive and that should be our cathode, that is not the reason why it should be in this particular case. And that is because we are given an actual reaction, yes? So we should actually look at the reaction and see what is happening here. Maybe you're still right. You probably are, but maybe you're still right. But in this particular reaction, because they gave it to us, we should actually look at it. Is probably why they gave it to us, I'm imagining. So the oxidation state here is +2. This is 0. This is 0, and this is +2. So when we look at the copper, which everybody wants to be our cathode, it is starting at +2 and ending at 0. Oh, you got very lucky today. That's good. It is actually the one being reduced. So it is actually your cathode, but for that reason, not your reason, you in general, nobody you in particular, but I pointed generally over there to the people walking in the hallway. And then obviously here, if we look at the iron, it is going from 0 to +2, so it is being oxidized. So in this case, they did give us a reaction. You should make sure you look at it. It may not always be that is the positive one. So you make sure that you do check the reaction. So now that we checked the reaction and confirmed that our copper here is our cathode, we could calculate our delta G, which is what we're looking for here, as minus NFE. And that is E of our cell. So we do need to calculate that, E of our cell. And I'm going to subtract here, so I'm not going to change any signs. So I'm going to take my cathode, which is 0.34 volts, minus my negative 0.44 volts, I believe. And that's going to get me 0.34 minus a minus 0.44. Going to give us 0.78 volts in this case, right? So now I'm going to put that into my delta G. And we're going to go minus our N. Our N is going to be 2, right? Again, we're not going to add those together. So just the 2 electrons is going from the copper, or whoever's going from the iron to the copper in this case. So it's going to be 2 moles. Our Faraday's constant is a constant 96,500 joule per volt per mole. And we're going to times it there by our voltage. Volts will cancel, moles will cancel, going to leave us again here joules when it's all said and done. That's going to be 0.78 times 96,500 times 2, going to yield us minus 150,540 joules. We'll turn it into some kilojoules, maybe like a $1.51 there. We'll go kilojoules in this case. Now, these two things do agree, right? So I got me a positive E. I got a negative delta G, and that means this reaction is spontaneous or non-spontaneous. It is spontaneous, yeah. Which again means we would expect this reaction probably to be heading in that direction, right? When it's all said and done. Question on any of that things. Well, that seems like a good thing to think about till we get here.